Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 7.4, the rational zero theorem and the fundamental theorem of algebra. Video 1, locating possible rational zeros. This is a follow-up to what was supposed to be the last question, or last type of question in homework 7.3. I'm not going to reiterate everything that I posted in the announcement, but the last three questions in homework 7.3, 14, 13, and 12 were supposed to be like question 11, the one prior to it. So really, there's only one question in your homework from 7.3 that is going to transition into this next section, and that question looks something like this. Previously in homework 7.3, we saw questions like this. Given f of x equals 3x to the third power plus 22x to the second power minus 30x minus 7, factor f of x, given that -2 is a 0. I hate this statement that has two givens in it, but I think I copied it directly from the homework. But regardless, we were asked to factor this function that has 4 terms but won't factor by grouping. Here we go, 4. However, when we were told that -2 is a 0, then we can use the factor theorem from section 7.3 that said the following. It said a lot of things. And let's bump this font size up a little bit. But the factor theorem from the previous section said that x equals c is a 0 of f of x if and only if x minus c is a factor of f of x, which are also all equivalent to saying that f of c is equal to 0. So really it's a three-way biconditional, which I guess makes it a triconditional. But let me throw an if and only if in here. If and only if. That's the worst spelling of only ever. So in other words, all the factor theorem says is that these three things go hand in hand. You are a 0 of the polynomial function. X minus c is a factor of the polynomial function, and c is a 0 of the polynomial function. Well, that's what it means to be a 0. So really this last thing here and this first one here are really synonymous because that's the definition of what it means to be a 0. So we're going to take off that third part of this. Whoa, come back, please. We're going to take off this third part of this triconditional. All right, so you're a 0 if and only if you have a factor. So zeros and factors go hand in hand. That's all the factor theorem says. So when we're told that when we're told that -2 is a 0, -2 is a 0 of f of x, this implies that x minus -2 or x plus 2 is a factor of f of x. Now, I've just painted myself into a corner and you don't realize this yet, but sometimes I set up these videos in advance. Don't look too fast because I'm going to go through them pretty quickly, but I've already got all the pages set up for this video, which means I did not leave room to actually do what I was asked to do in this question, which was to factor the polynomial function given that -2 is a 0. So I'm going to do this. And it will make more sense if somebody reads the PDF, but I'm going to say go to page 12, because when I add a new page, which I'm about to do, it adds it after the last one's already created. So I got to go all the way back here to see this function 322, -3, -70. F of x equals 3, 22, -3, -70. I only needed to remember the coefficients. I know how the powers go. 3x to the third plus 22x squared minus 3x minus 70. I believe that's what it was. I'm going to go back and check it just to make sure. 322, -370. 3, negative 22, negative 370. And our factor is x plus 2. All right, let's type this. Since x plus 2, look at that's in blue, how pretty. Since x plus 2 is a factor of f of x, we can divide f of x by x plus 2 to get the other factor. Using division. Now, we can use long division or we can use synthetic division, but this is tailor-made for synthetic division because we're dividing by something of the form x plus a number, x minus a number. Just remember, when you set up synthetic division, the number that goes in the box is the opposite of the number in the divisor. So a negative 2 will go into the box. The top row is the coefficients of what we're dividing into. So 3, 22, negative 3, negative 7. Now, I better get a remainder of 0 because this is supposed to be a factor. It divides evenly. Just remember how synthetic division works. Bring down the first number to get 3, multiply by what's in the box. What's in the box is negative 2. 3 times negative 2 is negative 6. Add vertically, 22 and negative 6 is 16. Multiply diagonally by the box number. 16 times negative 2 is negative 32. Add vertically, negative 3 and negative 32 is negative 35. You do not have to draw the arrows. That's just me pointing the direction I'm going. Multiply diagonally by the box number. Negative 2 times negative 35 is positive 70. And as expected, we get a remainder of 0. And remember, when you do a synthetic division problem, you are answering a division problem, and the answer to the division problem can be found in the bottom row except for the last number, because the last number is a remainder. So this means that our quotient is 3x squared because we start 1 degree less than we started. This polynomial starts with x cubed, so its quotient will start with x squared, since we're doing synthetic division, plus 16x minus 35. So what does this tell us? Well, this tells us that f of x is equal to x plus 2, which is what we divided by. And on the bottom row, we got 3, 16, negative 35, 3x squared plus 16x minus 35. Now, will this factor further? Possibly. What were the instructions on page 2? Way back here. Factor that. Okay, well, technically it's factored, but is it factored completely? Will this factor? If it does, then we're expected to factor it. If it's not, then we're finished. Let's see, can I insta-factor this? So let me think about this for a second. I might be able to insta-factor this if it factors at all. I know it would have to be 3x and x in the first part because that would have to give me the 3x squared up front. So not many choices there. And the 35 only has a couple of ways I can break down. I can break it down into 1 times 35 or 5 times 7. But keep in mind that I have to create a 16 when I combine the outside and the inside parts of the full process. So can I drop numbers in here to create a 16? 5 and 7. No, 5 and 7 doesn't work either way. I doubt 1 and 35 will work. I'm pretty sure this is prime. I'm pretty sure 3x squared plus 16x minus 35 will not factor. Well, let's just try it. If I put a 5 and a 7 here, then the outside makes it 21. Oh, of course it'll factor. It's right there in front of me. Let's see. And I say that because this is 21x on the outside. This is 5x on the inside. I can combine those to make a negative 16 if the 5x is negative and the 21x is positive. So the 7 has to be positive since it made the 21, and the 5 has to be negative since it made the negative 5x. So our function does factor completely into x plus 2, 3x minus 5, and x plus 7. There is an alternate way to get the last two factors where you multiply, and I'm not going to do it here, but where you multiply these guys to make a new product. The number in the middle is your sum. Figure out the two numbers that add and multiply correctly. Split the positive 16x into this and that, and then factor by grouping. But the intent of this part of the video was to show you the following. If you tell me something, go back to page 2, like -2 is a 0 of the function, then the factor theorem tells me that x plus 2 is a factor. And then we can divide, like we did here, to find the other factor, which was 3x squared plus 16x minus 35, and then use that information to not only factor the function, but try to factor it further. The answer downstairs, down here, is your final answer. Well, not including that plus 21x. That's just residual work from the previous step. There we go. All right, but that's not the real question. This is just what happened in 7.3. When we're told something like -2 is a 0, but it begs the question, how can we factor f of x if we were not given that -2 is a 0 of f of x? We wouldn't know what box number to use in synthetic division. This video explores how to analyze the original function to locate possible zeros of f of x. All right, so we're going to reverse engineer some things. We're going to retrace where the -2 was embedded in the function. I'm going to take the results that we got from the synthetic division problem, which were when we divided the function by x plus 2, we got 3x squared plus 16x minus 35. And let's keep in mind that this -2 came from this factor. By putting x plus 2 equals 0, move the 2 to the other side, we get x equals -2. But let's keep track of the -2 as we re-multiply this. Now, to re-multiply it is not nearly as bad as it seems, because all we have to do is a couple of distributions. Number one, we have to distribute the x. Excuse me, didn't mean to erase stuff. Number one, we have to distribute the x across the second parentheses. And number two, we have to distribute the 2 across the second parentheses. Now, if we do that, here's what we'll get. When we distribute the x, we get 3x squared plus 3x cubed. X times 3x squared is 3x cubed, plus x times 16x is 16x squared. And then minus, or x times -35 is -35x. And notice we haven't touched the 2 yet. We haven't touched this 2. All we've done is taken the x in front of it and distribute it. So none of the numbers that I wrote down yet contain the 2 hiding inside of it. Now, by contrast, every number that I'm about to write will contain the 2 inside of it. +2 times 3x squared is +6x squared. +2 times +16 is +32x. And +2 times -35 is -70. 1 second, I'm going to change something. I just changed the font color on the last line to match the colors of the little arcs used to represent the distribution. So that when I distributed the x, it got distributed using blue arcs, hence the blue down there. And when I distributed the 2 underneath, I distributed it using kind of brownish arcs, and so brown right there. But remember, what we're trying to do is to keep track of where the 2 went, and the 2, when it got distributed, is in there as a factor, in here as a factor, and in here as a factor. So yes, 2 divides all of those. But if I were to finish combining things, the only x cubed term is the first one, and it didn't have the 2 to begin with, so that doesn't tell us anything. However, I have 2x squared terms. My 2x squared terms are +16x squared and +6x squared. And when I combine them, I get +22x squared. Now, the 22 was inside of the 16, but the 6 here, but it just got added to the 16 to make the 22. So I just lost track of the number that was containing the 2. I lost track of the 6 because it got added to create that 22. And you might be thinking, but 22 is a multiple of 2. That was a coincidence because the 16 here was even. Let's find our x terms. And this will really make my point. There's a negative 35x from the distributing the x. There's a positive 232x from distributing the positive 2. Now, the 32x does contain the 2 as a factor because I did 2 times 16 to get 32. But when I combine those highlighted like terms, I'm going to get negative 3x. And why is that a problem? Well, one of the things that had information about the 2, this guy right here, just turned it into something that doesn't have a 2 in it at all. So we totally lost sight of where that 2 went in that term. But notice that the last term is the only constant term, the negative 70. And so that negative 70 is still there in its original form. And that negative 70 originally came from 2 times negative 35, excuse me, from 2 times negative 35. So there is one number in my function that contains the 2 that was part of the factor x plus 2. It's the 70 at the end. The other numbers that contain the 2 got combined with other like terms, and we lost sight of that too. But 2 is a factor of 70. And so all along that 70 said, hey, 2 is a factor of me. So if there was a multiplication problem that happened, there might have been a 2 involved. And if that 2 is involved, as it is in here in the first factor, then that means that 2 could be a 0, or negative 2, I should say. Okay, so to summarize everything I just said, the number that I was given was embedded inside of the 70 all along. So that's a hint as to where we can look when we are not given something like negative 2 is a 0. Don't worry, this is all going to be polished up here soon. All right, this suggests that factors of the constant term are possibly zeros of f of x. Let me say that again, but go back here. This suggests that factors of the constant term, in this case 70, and one of the factors of 70, or negative 70, is negative 2. Now, we'll worry about negative and positive signs later. But this suggests that factors of the constant term are possible zeros of f of x. But what if a 0 is a rational number, in other words, a fraction, but not an integer? Well, we're going to retrace that also. So, and we're going to do this one a little more easily because we already have a function that is factored and has x equals negative 4/7 as a 0. Now, if it's not immediately obvious that x equals negative 4/7 is a 0 of this function, then what would happen if you ask yourself, what would happen if I put 7x plus 4 is equal to 0 and solved it? Well, the 4 would move over and become negative, and then we would divide both sides by 7. So yeah, it is possible to reverse engineer a 0 back into a factor. In fact, that's part of what the factor theorem says. So this function does have x equals negative 4/7 is a 0. Now the other factor, the 2x squared, I just undid something and I didn't mean to. Hope that's nothing catastrophic. The other factor, the 2x squared plus x plus 3, I'm not worried about it. It actually won't factor. It's stuck as is. But we're going to keep track of where the 7 and the 4 go when we re-multiply all of this. So let's do the same thing we did before. First thing we're going to do is distribute the 7x across the second factor and keep track of all the terms that have 7s. 7x times 2x squared is 7x cubed. 7x times x is 7x squared, or I should say positive 7x times positive x is positive 7x squared, and then positive 7x times positive 3 is positive 21x. And all of these clearly have a 7 inside of them. But what happens when we distribute the 4? Well, we get 4 times 2x squared, which is positive 8x squared. Positive 4 times positive x, which is positive 4x, and positive 4 times positive 3, which is positive 12, all of which clearly have factors of 4. And remember, what we're attempting to do, and it's got a little bit drawn over there, so I'm going to fix that real quick. But what we're, come back, please. What we're attempting to do is keep track, if I can stop erasing things, keep track of, come on, stop it. Keep track of where the 7 and the 4 went that represent the 0 of the function. All right, so the 7, on the bottom line, the 7's in all the brown terms, the 4's in all the blue terms. But when we start combining like terms, we run into a problem. Well, not all of the like terms, but some of them. For example, the only x squared term is, x cubed term is 7x cubed. So that's not going to change. There will still be a 7x cubed up front. I'll make that 3 a little bit better. But we have a positive 7x squared term and a positive 8x squared term. The first one has the 7 embedded in it. The second one has the 4 embedded in it. But when I combine them, I'm going to get positive 15x squared. And 15 contains neither 7 as a factor nor 8 as a factor. So by combining those like terms, I totally lose sight of the 7 and the 4 that we're keeping track of. And the same thing happens over here when we combine the plus 21x, which has 7 as a factor, and the plus 4x, which has 4 as a factor. When we combine those, we get plus 25x, which has neither 7 nor 4 as a factor. So it seems like whenever we combine these like terms, we totally lose sight of the factors that we're trying to keep up with, which in this case is the 4 and the 7 from x equals negative 4/7. However, the last term is the only constant term, 12, which came from 4 times 3. So that term survived. And now we can kind of summarize where the 7 and where the 4 went when we took the x equals negative 4/7, rebuilt this factor, and then busted it all open to get this. Where did the 7 and where did the 4 go? Well, the 7 is pretty obvious. The 7 is here. Hold on. This has a factor of 7. It is 7, but 7 is a factor of itself. And the 4, if we backtrack it, it went all the way back to the 12. So this has a factor of 4. So what does all this mean? Well, what all this means is if we have a rational 0, meaning a ratio of integers, and by the way, even something like x equals negative 2 is a rational number because we can put it over a 1. So we can stop saying integer or rational and just say rational, since that includes all the integers. So if we have a rational 0 like negative 4/7, and we know it came from a factor like 7x plus 4, then that 7 and that 4 are embedded in the original function at the front end and at the back end. So what does all this mean? Well, here's what it means. From this, we propose the following. It should be mentioned that the following is indeed true, but our one example doesn't prove it. What is it? Well, it's something called the rational 0 theorem. And it basically says in words and symbols what we just said here, that the 4 in negative 4/7 is embedded in the 12, and the 7 in the negative 4/7 is embedded in the 7. More generically, the numerator of the 0, in this case 4, I know it's negative, but we can worry about that later. The numerator of the 0, 4, is a factor of the last term, the constant term. And the denominator of the 0, 7, is a factor of the leading coefficient, the number in front of x cubed, which is what the rational 0 theorem says. If f of x is a polynomial function with integer coefficients, the grammar is bad here. If f of x is a polynomial function with integer coefficients, there's supposed to be a comma there. That's the issue. Comma has a leading coefficient of a, which I'm calling capital A. In this problem, the capital A is the 7 in front. And a constant term of b, the constant term is the term without any x's. In this case, our b is 12. then every rational zero of f of x has the form b over a, little b over little a, where little b is a factor of big B and little a is a factor of big A. It's at this point that some of you are like, I have no idea what you just said. So let's translate it. In other words, integer or fraction solutions of that equation. Whole numbers or fractions that make the function equal to 0 when you put them in have the following form. And here's the kicker. Factor the constant term over factor of the leading coefficient. Leading, hold on. Factor the constant term over factor of the leading coefficient. And this is really actually easy to set up. Now, I was planning on doing all this, but we're going to do that in part 2 of this video. This video has already gone on pretty long.